We are continuing to look at outlier models, and just a refresher in case you missed the previous video, when it comes to outlier models, we can detect anomalies, fraud, with support vector machines by having one class. So a classification model means we have labeled data, so we know whether or not it's fraud or not, anomaly or not, and so then we can train the model based on that. If we're looking for spam, we're looking for anomalies in text, so anything that is not an actual conversation but is instead a phishing expedition. We can do multinomial naive Bayes for text analysis. In our previous video, we looked at dbScan, which is a cluster analysis method where it looks for what's in the cluster, and then if we get a -1 label, then we identify it as an outlier. So we can use that for detecting fraud as well. Now, the other methods we're going to look at is one, Benford's law, which is the focus of this video. And then in our next video, we'll look at forecasting models to help identify outliers as well. So let's start with Benford's law. Benford's law, also called first digit law, uses the same mathematical laws as Zipf's law. So that's a lot of words. But in our text mining videos, we talked about Zipf's law, and we use Zipf's law to identify whether or not communication, if you remember, in our generative AI documents was efficient. So we looked at the guidance on generative AI coming out of Canada, out of the US, and out of the EU to see who was more efficient in their language. So when we look at the language, logistics, efficient communication is where the most common words appear twice as often as the second most common, 3 times as the third, and so on. So we get this exponential decay where it drops quite quickly as we go from the most common word down to the least common word. So the magnitude of words tends on the whole to stand in an inverse, not necessarily proportionate, relationship to the number of occurrences. And you'll recall when we talked about Zipf's law, Zipf came up with this, right, when he actually manually counted, and you can't see this because my face is covering it, but he actually manually counted the 260,430 words in Ulysses by James Joyce, and that's how he discovered this relationship. So when we look at it in a text, in a linguistics perspective, if it's not in alignment with Zipf's law, it's considered to be redundant, long-winded, or circular. We can apply this similar law to numbers. And so that is called Benford's law, or first digit law. And the idea here is that real life sets of numbers have this same exponential decay, where the number 1 appears way more often as the first digit than the number 9. So if it's actually based on real life generated the data, the number 1 is going to be way more frequent than number 9. For example, number 1 here appears 30% of the time, while the 9 appears less than 5% of the time. What happens is that when humans start, generating numbers off the top of their head, they tend to favor certain numbers like 7 and 9. And so when we look at numbers that have been fabricated, they don't tend to follow Benford's law. So we can actually use Benford's law to help identify fraud in financial reporting by taking all the numbers in a report and looking at the first digit, and then plotting them like we see here, and then adding to it the same line, the same curve like we did in Zipf's law, this one, Benford's law. So let's do that. All right, here's how we do that. We are in the outlier notebook under the section called fraud detection using Benford's law. And I'm just gonna move my face back down here. Okay, now, I'm using a data set here. This is originally an Apple financial statement that I then played with. So I added some and fudged some numbers here. So let's see if we can tell what has been done. So as we look at this offhand, right, it looks okay. Total revenue, cost of revenue, gross profits. The numbers seem in order when you look at it. They're of legit size for the company. They are consistent, it looks like, from year to year. All right, so let's look at, first of all, if you want to do this along with us, then to do this along with us, so let me back out here. We are at drstephpowers.github.io/BIA. There you will find this outlier detection workbook. And when you go in the outlier detection workbook, come on. Oh. Then what it will do is it'll take you into GitHub, and then you can go to the data folder and you can pull this little file from the data folder. All right, so this little file called Apple. Okay, so I have taken this little file called Apple and I have put it into my Google Drive. And just a reminder that if you are doing this as well, save a copy of your workbook into your Google Drive and then mount your Google Drive into your workbook so that you can then call your data sets. So we've mounted that drive and now we can load in Apple and we can look at the Apple data. So here we have for the last couple of years, the financial report in terms of revenue, gross profit, operating income, and so on. So to do Benford's law, what we need to do is we need to basically make a list of all the numbers that are on our text page or in this, our spreadsheet. What we want to do is take all the numbers. So we have a command here called concat, and it's just going to take this column. So Apple's name of the table, 2023 is the name of the column. Because it's a number, when you put it in quotes, it doesn't like that here. It thinks it is a number. So you'll notice there's no quotes around it, even though it is the name of the column. So Apple 2023, comma, Apple 2022, Apple 2021, Apple 2020. It's going to simply take those columns and stick them one after another in what we see here. The other thing we have is when we look at the actual data, there are numbers, right? Years, times when we are losing money, where things are subtracted. And so in order for Benford's law to work, we need to get rid of the negatives. So the first step we do after we combine all these columns of numbers is to take the absolute value. This will get rid of the negatives in front of that. All right, so here's our data. In order to pull just the first digit from each of these numbers, we're actually going to have to first convert it into a string. We need it to think of it as text. And so if it thinks it as text, we can pull the first letter. Well, in this case, we're going to pull the first number, but we're going to take our app here, change the type to string, so as type string. And then we're going to do .string:1. That's going to pull just the first digit. And then we can output that. So you can see here we have our first digits. Okay. So we've gone from a list of all the numbers to just the first digits of all those numbers. Now, sometimes in this process and in the data set itself, you might have dashes. It doesn't like that and it will get grumpy about it. So if you keep getting an error, make sure you do something like remove here any of the dashes there. And then the other thing we need to do is turn it back into an integer because we don't want it as text, we want it as numbers. So we are going to apply integer to convert it back. But you can't apply this integer and convert it back if there are spots where it has just a dash. It doesn't know what to do with those, okay? It's looking for things that are numbers, right? So it's going to complain if it comes across things that are not numbers. So just recognize as you sift through, if you're getting an error when you try to turn it into an integer, that may be because somewhere in your list there's something that's not a number that can't be turned into an integer, so you need to get rid of it using this method here in order for this to work. Otherwise, it'll just complain to you. All right, so the next thing we're going to do is we are going to take these numbers, and I want to count how many times the number 8 appears, count how many times the number 5 appears. And so we're going to do value counts. We've seen that before. And then we're going to sort it. And we're going to sort it by the index because we want to know how many 1s, how many 2s, how many 3s, and so on. So let's get our table here. Now, if we plot this information just offhand, we are going to do plt.plot. We're going to have the index numbers here. That's the 1 through 9 on the horizontal. And the values from our frequencies here on the vertical. We'll just get rid of the tick marks on the X's. Doesn't really matter. All we really care about is shape here. And so let's look at the graph. So I plot this graph. Notice that already we can see there's issues, right? It doesn't have that nice exponential decay. In fact, it comes up, and then we have this peak here. And that's because when, people fabricate numbers, they like things like 7s and 9s. And so here's these bumps that you see here. All right, so how do we then apply Benford's law? What we want to do is we want to add an image to this graph that shows what it should look like if it is truly following Benford's law. So we're going to use from skippy.interpolate, we're going to import make interp splines. So we're doing this because we're using this function here that uses splines. And what it does is it takes our actual data and says, based on our actual data, here's what the curve should look like, and it's building it based on splines, which are kind of little pieces of a curve. All right, so we're going to take this function exactly as it is. This is the same function that we had from Zipf's law. So we're just going to import this function fully. And even this line here where it says Zipfian curve values, I didn't even bother to change it. The only difference from what we had before is that we're doing this freq.index goes here instead of the index of our word count. So we're just changing that. But if you really wanted this to be multi-use, put this inside of a function and then put a placeholder here so you could just keep reusing it. So you could actually just create a function that uses this function and then does this calculation. So embed your function in a function, and then it's truly reusable everywhere else instead of having to change this line here. We can then call our smoothify function using our Zipfian curve values and our frequencies that we've calculated from our data here. And this gets what the curve would look like based on our numbers if it really had that exponential decay that the Benford's law or Zipf's law says it should have. So this is creating the ideal image, and then we'll compare it to the actuals. So we need to do a little bit of an adjustment here for our data. We're going to take our original data and rescale it so that it goes from 100% down. So that's what this piece here is, to just help rescale ours so that we can lay the two on top of each other. So let's do that. And then we create our plot. So the first line of the plot is going to be the curve based on our financial data. And then the second one is going to be the ideal based on Benford's law. We could then color code them numbers and Benford's law. We can have X ticks if you want. Y label percent frequency, X label index. So if you want to see it labeled, maybe I'll remove this here. And then you can see the numbers. Okay. So you can see here, like here's 9, and it looks like here we got a bunch of 5s that shouldn't exist. 4 is a bit too low. So what you see in the orange is the Benford's law ideal. And then when you start to see kind of wonky pieces, like here the 4s are too low, here the 9s are too high, that's telling you that likely that some of the numbers have been made up. So we can use this to flag potential fraud in financial statements.